The atom can be thought of as a nucleus with protons and neutrons surrounded by fast-moving electrons. In the science of chemistry, much attention is given to the arrangement of electrons in the atoms of the elements because the behavior of electrons influences the bonding or joining together of atoms to form molecules. While electrons are repelled by other electrons, they are attracted to protons. They orbit the protons in the nucleus without crashing into it, much like a satellite orbits the Earth. Electrons arrange themselves in orbits similar to the way the planets orbit the Sun. They fill up orbitals in a definite pattern governed by a set of rules discovered in the early 20th century called quantum mechanics. Orbitals are like volumes of space around the atomic nucleus in which electrons are likely to be at any instant in time. Different energy levels are associated with the orbitals, and each orbital can contain either one or two electrons. Orbitals can be thought of as occupying shells around the nucleus. The shell closest to the nucleus has one orbital holding a maximum of 2 electrons. The next shell can have 4 orbitals with 2 electrons each for a total of 8 electrons, and so forth. They seek the first available orbital that takes the least amount of energy to occupy. Generally, it takes more energy to occupy higher orbitals. Of particular interest to chemists and physicists studying the behavior of electricity is the outermost electrons in the atom, called the valence electrons. The electrons of different types of atoms have different degrees of freedom to move around. The outermost or valence shell electrons in a copper atom is very easy to remove. With some types of materials, such as metals, the outermost electrons in the atoms are so loosely bound that they chaotically move in the space between the atoms of that material by nothing more than the influence of the room temperature heat energy. Because these virtually unbound electrons are free to move about their respective atoms and float around in the space between the adjacent atoms, they are often called free electrons. In other types of materials, such as glass, the atom's electrons have very little freedom to move around. While external forces such as physical rubbing can force some of these electrons to leave their respective atoms and transfer to the atoms of another material, they do not move between the atoms within that material very easily. This relative mobility of the electrons within a material is known as electric conductivity. Conductivity is determined by the type of atoms in the material, the number of protons in each atom's nucleus determining its chemical identity, and how the atoms are linked together with one another. Materials with high electron mobility, many free electrons, are called conductors, while materials with low electron mobility, few or no free electrons, are called insulators. Here are a few common examples of conductors: silver, copper, gold, aluminum, iron, steel, brass, bronze, mercury, graphite, water with dissolved impurities, and concrete. In general, metals are the best conductors of electricity. A few common examples of insulators are glass, sulfur, rubber, oil, asphalt, fiberglass, porcelain, ceramics, quartz, dry cotton, dry paper, dry wood, plastics, air, diamond, and pure water. It must be understood that not all conductive materials have the same level of conductivity, and not all insulators are equally resistant to electron motion. Electrical conductivity is analogous to the transparency of certain materials to light. Materials that easily conduct light are called transparent, while those that don't are called opaque. However, not all transparent materials are equally conductive to light. Window glass is better than most plastics and certainly better than clear fiberglass. So it is with electrical conductors. some being better than others. For instance, silver is the best conductor in the conductors list, offering easier passage for electrons than any other material cited. Water with impurities and concrete are also listed as conductors, but these materials are substantially less conductive than any metal. The physical dimension also impacts conductivity. For instance, if we take two wires of the same conductive material, one thin and the other thick, the thick wire will prove to be a better conductor than the thin for the same length. If we take another pair of wires, this time both with the same thickness but one shorter than the other, the shorter one will offer easier passage to the electrons than the longer one. This is analogous to water flowing in a pipe. A fat pipe offers easier passage than a skinny pipe, and a short pipe is easier for water to move through than a long pipe, all other dimensions being equal. It should also be understood that some materials experience changes in their electrical conductivity properties under different conditions. Glass, for instance, is a very good insulator at room temperature, but becomes a conductor when heated to a very high temperature. Gases such as air, normally insulating materials, also become conductive if heated to very high temperatures. Most metals become poorer conductors when heated and better conductors when cooled. Many conductive materials become perfectly conductive. This is called superconductivity at extremely low temperatures. The normal motion of free electrons in a conductor is random, with no particular direction or speed. Electrons can be influenced to move in a coordinated fashion through a conductive material. This uniform motion of electrons is what we call electricity or electric current. To be more precise, it could be called dynamic electricity in contrast to static electricity, which is an unmoving accumulation of electric charge. Just like water flowing through the emptiness of a pipe, electrons are able to move within the empty space within and between the atoms of a conductor. The conductor may appear to be solid to our eyes, but any material composed of atoms is actually mostly empty space. The liquid flow analogy is so fitting that the motion of electrons through a conductor is often referred to as a flow. A noteworthy observation may be made here. As each electron flows uniformly through a conductor, it pushes on the one ahead of it, such that all the electrons move together as a group. The starting and stopping of electron flow through the length of a conductive path is virtually instantaneous from one end of the conductor to the other, even though the motion of each electron may be very slow. An approximate analogy is that of a tube filled end to end with marbles. If you put a marble in one end of a marble immediately comes out the other end. Thanks for watching.